Good morning, students. Today we're going to see steps to design Butterworth filter, that to digital Butterworth filter using bilinear transformation technique. Okay. First step, as I already mentioned in the last class, when analog omega is equal to digital omega, in other words, when analog frequency is equal to digital frequency, at higher frequencies, it has been observed that distortion will be introduced both in digital design as well as analog design due to non-linearity. That effect we call it as wrapping effect. It has to be overcome with help of pre-wrapping. So as a result, the first step in designing a Butterworth filter using bilinear transformation technique is to pre-wrap the frequency. So first step is, now even in the same thing is true even if you designed Chebyshev filter. Okay. So we need to pre-wrap. Pre-wrap what? Pre-wrap the frequencies. Okay. In general, they'll give us digital specifications, that is Kp, Ks, omega p, omega s, digital omega p, digital omega s. We need to pre-wrap it. How? With the help of this particular formula. Omega p star is equal to 2 by t times of tan of omega p by 2. Omega s star is equal to 2 by t times of tan of omega s by 2. Where digital omega p is equal to analog omega p into t. Digital omega s is equal to analog omega s into t. Once you find this, from here onwards, we need to use the same formulas. Okay, that is omega p star as well as omega s star. The next step is to find out order. Okay, since this is Butterworth filter design, n is given by 10 log of 10 power minus kp by 10 minus 1 divided by 10 power minus ks by 10 minus 1 divided by 2 log omega p star by omega s star. See, if you observe here, we have used pre-wrap frequencies. Okay, suppose if you are designing high pass filter using BLT technique, there is slight change in formula. Here it is 2 log omega s star by omega p star. Okay, n is given by log of 10 power minus kp by 10 minus 1 divided by 10 power minus ks by 10 minus 1. This will remain same here, omega s star by omega p star. Once you find out the order of filter, the next step is to find out the poles. How? That is with the help of this particular formula. Sk is equal to e power j into theta k, where theta k is given by pi by n into k plus pi by 2n plus pi by 2, where k varies from 0 to 2n minus 1. Okay, out of which we need to consider only first 50%. The reason is we need to consider only left half poles. Once you find out poles, find the transfer function, which is given by hn of s is equal to 1 by summation left half poles s minus sk. Okay, use this particular formula and find out transfer function. Once you find transfer function, that transfer function, that what you have designed till here, till that step 4, is nothing but the transfer function corresponding to normalized filter. What do you mean by normalized filter? Normalized filter is one when in omega p is equal to omega c is equal to 1 radians per second. Suppose if they gave omega p value as 1 radians per second, then this much data is sufficient. Sometimes omega p value may not be equal to 1 radians per second. At that time, we need to apply suitable analog to analog transformation, or we need to denormalize it. How? For that, we need the formulas for cutoff frequency. The formula for cutoff frequency is given by one of this. If we desire to meet our requirement at passband and do better than stopband, then we'll use this. Omega Cp is equal to omega p star divided by 10 power minus kp by 10 minus 1 whole power 1 by 2n. Omega Cs, suppose if we desire to meet our requirement at stopband and do better than passband, then we'll use this second formula. That is omega Cs is equal to omega s star divided by 10 power minus ks by 10 minus 1 whole power 1 by 2n. In some cases, we'll take average of them. That is omega c is equal to omega cp plus omega cs by 2. Next step is to denormalize it with the help of this cutoff frequency to obtain suitable filter as per the specification. Now, for that filter transfer function, what we need to do is we need to up to step 6 we'll get denormalized analog filter transfer function. But basically through BLT we'll design digital filter. How? With help of this transformation. That is, if you want h of z through bilinear transformation, then ha of s, in ha of s, s has to be replaced by 2 by t times of 1 minus z power minus 1 by 1 plus z power minus 1. Substitute this and further simplify. Sometimes they'll give you the value of t directly. Sometimes they'll give f, which is sampling frequency. From that you need to find out t. In some cases they won't give you the value of t. At that time consider it as 1 second. Hope you have understood the steps. Thank you.